One.
Yeah. Welcome everybody to this edition of the String Seminar. It gives us a great pleasure to have Nima Arkani-Hamed with us today, and he's going to tell us about space-time quantum mechanics in Clusterhedra at infinity. Over to you, Nima.
All right. Well, it's really wonderful to be able to join so many old friends here on Zoom. Thanks so much for the invitation. I'm talking about a kind of line of investigation that I've been pursuing with the many friends here that are all listed. A wonderful group of physicists and mathematicians over the past decade or so, really. But a new perspective on this subject has emerged in the last 2 or 3 years. That's greatly extended the scope of the kinds of theories that can be talked about in this way, and the specific new ideas about this concept of clusterhedra that I'll hopefully get to towards the end. I want to sort of set the stage more just so you understand what's going on. But those ideas are being developed now and work in progress with my friends, the mathematicians Hugh Thomas and Pierre-Guy Permondon, and the really wonderful young physicists Giulio Salvatore and Hadley Frost. Okay, so I'll begin with some quick context, which for string theorists can go very quickly indeed. We've known for a long time that when we have in some sense, we've known since the 60s that when we have quantum mechanics and gravity, the only observables that we're allowed to talk about live on the boundaries of space-time. And since gauge gravity duality, we've had one very precise instantiation of this, which people have been exploring intensively for over 20 years now, and will keep exploring intensively. There's a lot left to understand about it. But where we have this idea of a quantum mechanical system that lives on the boundary of empty de Sitter space, holographically encoding a theory of gravity that lives in the bulk. And so this is an example where from just quantum mechanical theory on the boundary, space and gravity and everything else emerges in the interior. But a crucial part of the story is that time is left alone. The time that flows on the boundary is the same as the time that flows in the interior. And that's why in the end, this is an equivalence, it's a duality between two physical systems that are otherwise described in ordinary standard physical language of time evolution. So space and gravity emerges, time is left alone. But of course, the real world isn't particularly close to empty de Sitter space, especially these observables. We could say that the curvature of we could ignore the fact that the world is cosmological and sort of imagine the curvature was ridiculously low, and approximate the interior might not look too different from empty de Sitter space, but the observables that we care about in the real world are not close to the observables that we think of as boundary observables in empty de Sitter space. So when we get closer to talking about the real world, one significant step closer is to talk about flat space. And here the boundary observable are scattering amplitudes. We could talk about cosmology, where the boundary observable are cosmological correlation functions, or more pretentiously, the wave function of the universe. But there's a big difference between this situation and what we've gotten used to in ADS, that here, if you decide to take this sort of holographic mindset and go to the boundary at infinity, it's not obvious what to do there. And the reason is that unlike in empty de Sitter space, the boundary of flat space or the cosmological boundary does not have any obvious notion of locality or of time. And so if we're going to take this attitude of sort of looking for a theory that doesn't have the interior of space-time in it, but gives us the observables anyway, we necessarily have to be more adventurous. And this is speculative, but I think we've been seeing in this line of investigation for the past 10 years, more and more evidence for this picture that what's really going on is that there's some more abstract set of ideas in this question mark. And out of them, we can see to emerge the rules of quantum mechanics and of space-time kind of joined together as two sides of the same coin, but fundamentally joined in an interesting way. So we'll see some more concrete examples of that in the talk today. So if we go back to the question of scattering amplitudes, this is again just phrasing the same problem.
Nima,
just imagine.
Sorry, could I ask? Is your picture that there's a sort of Hilbert space on that boundary, or is it some more abstract concept?
No, something even more abstract still. That's really the point, is that it's not a Hilbert space, it's not space-time, and something else. There is another question whose answers we can then interpret as being local and unitary. And that's very speculative, but if you're not going to have time, it's not obvious why you have quantum mechanics. That's part of the problem. So that's part of the challenge of this entire subject, is that it might be too radical. Maybe we can do something. Maybe we can do something less radical. But the sort of most obvious read of what you're supposed to do is find some question that doesn't have any of the virtual particles in it, doesn't have any of the interior of space-time in it. It's not going to have time. It's not obvious why it has quantum mechanics in it. And you want to get answers that you can interpret as being amplitudes that correspond to unitary evolution in a Hilbert space and local evolution in space-time. So that's what we're trying to do. And the reason it's not entirely pie in the sky is that when we start restricting to specific questions like scattering amplitudes, what locality is and what unitarity is at the level of the amplitudes is reasonably sharply understood, so that as sort of simple mathematical properties of these functions, so that we have a target. We can try to understand where those singularity properties and factorizations that we ascribe to local and unitary evolution, at least we normally explain with local and unitary evolution in space-time, we try to understand where those come from another point of view. So that's really what I was sort of saying in this slide here. If we just have the on-shell data at infinity, and we talk about this scattering process, then there's in the question there's no in the observation there's no interior of space-time, and there's no Hilbert space particularly either. You're just some simple-minded experimentalist throwing things in from infinity, measuring them at infinity. But you want to find what's in this black box that generates this process, and what's in this black box is a picture of local evolution in space-time and unitary evolution in Hilbert space. And we can think of this picture as explaining and sort of trivially giving certain singularity properties of the amplitude that are supposed to encode both locality, causality, as well as unitarity. But the precise question that we can ask now, or starting to get more precise question, is we want something else to go on this black box, and this something else should give us these rules of the singularity structure and factorizations of amplitudes as an output and not an input, so that at least we can begin to see how the rules of space-time and quantum mechanics, here more specifically, the locality and unitarity of scattering amplitudes can come out as derivative outputs from some more abstract set of ideas. And we'll see very precise examples of this. So a more practical motivation for these are very highfalutin motivations for doing this. More practical motivation that you've probably seen in every talk on scattering amplitudes is that if you actually compute amplitudes, even in perturbation theory, the way we need to describe the real world, for example, collisions at the LHC, or even collisions of high energy cosmic rays with the upper with atoms in the upper atmosphere, then the calculations quickly become incredibly complicated. Here's an example of what a sort of 2 to 3 gluon calculation would look like using Feynman diagrams. And yet, a little over 30 years ago, we started understanding the final answers. This is the famous Park-Taylor formula, for example, for the tree-level collision of 2 negative helicity gluons and 4 positive helicity gluons. The final answers are shockingly simple. And this is a much more practical indication that the standard way of doing this physics that makes the usual rules of space-time and quantum mechanics manifest, that's the purpose in life of path integrals and Feynman diagrams, that's perfectly correct. It's totally general. There's nothing, it's wonderful, but it's hiding something. It's hiding some extraordinary new structures. And 32 years ago, it was not obvious that this is the tip of a big iceberg. Today, we know it's the tip of a very big iceberg. And so what we'd like to do is understand where these things come from, and hopefully in doing that, since making space-time and quantum mechanics manifest hides all this structure, maybe understanding where the structure comes from can be inverted as a way of giving a deeper insight into the origin of locality and unitarity. Anyway, that's the dream. That's the big picture goal. Okay, so once again, we want to know what goes inside this black box instead of local unitary evolution. And for the last 10 years or so, and really more intensely in the past 2 years, we are seeing that there's a question that you can ask directly in kinematic space, in the space that defines the scattering process. There are questions that we can ask in that space that give us an answer that we can think of as amplitudes, and those questions involve new and interesting mathematical ideas that are broadly being referred to the idea of positive geometry in kinematic space, and we'll see some examples of that. So our canvas, so again, just to start to get more precise about what the challenge is, our canvas, what amplitudes are functions of, are maybe physical momenta. Let's say null momenta if we're talking about scattering amplitudes, or twistor variables, or points on the celestial sphere, or points in the spatial future if we're talking about the wave function of the universe. But in all these cases, again, unlike the boundary of anti-de Sitter space, which is a normal place with a metric, with the notion of time and locality, here it already seems much weirder. Like, what am I supposed to do in the space of n null momenta? I have to ask a question in the space of n null momenta, whose answer is going to be scattering amplitudes with all their richness and complexity. So that's the challenge. So we begin with what seems like very arid and boring and dry spaces, and we have to find some question to ask in these space that breathes physics life into them. And what we've been seeing is this emerging picture is that in this kinematic space, even though it seems to be very, very, very austere, there's natural combinatorial structures that live there that determine certain geometric subparts of these spaces, the positive geometries, that are in turn associated with certain canonical differential forms, which is where the functions come from that we can interpret as amplitudes. And anyway, the story is not remotely over, but that's the kind of emerging picture that we're starting to see. This was first seen in the context of the amplituhedron and n equals 4 super Yang-Mills amplitudes in the planar limit. More recently, in the past few years, really what happened around 2.5 years ago is that we understood how to think about the amplituhedron directly in kinematical space, directly in the space of the data that specifies the scattering process, and that was an important advance because it allowed us to start exploring the same kind of structure in completely non-supersymmetric other theories. So I won't be speaking about the amplituhedron at all today. I'll mostly be speaking about phi cube theory, this bi-adjoint phi cube theory, where the corresponding geometry is known as the associahedron, is related to existing, in some sense, simpler geometric objects. Amplituhedra are like sort of curvy generalizations of polygons and polyhedra, polytopes in higher dimensions. The things that are of relevance for phi cube theory, these totally non-supersymmetric theories, are just honest polytopes. So we'll just be talking about some simpler objects. I should say there's been some very interesting work done in India on generalizations of these kind of associahedron ideas to phi to the 4 theory, phi to the p theory in general, things known as Stokes polytopes and accordiahedra and so on. I won't have much to say about that. I'll be focusing on the bi-adjoint phi cube theory today. Anyway, so that's the rough picture which is emerging. But just right here, I want to stress that these aren't like totally random toy models that are very distant connection to the real world. These things actually describe the actual real world that we see outside our window in a reasonable approximation. And they expose hidden symmetries and new mathematical structures of things that again describe the world that we see outside our window. And to me, one of the most delightful aspects of the subject is just to see how much pure magic there is in physics that's sitting right under our noses, not in sort of faraway esoteric places, but physics sitting right under our noses. All right. Now, let me, because most of this talk I will be talking about the geometries, polytopes, geometries, and so on, let me just pause for a second to tell you a little bit about what this idea of positive geometries is. So here's what a positive geometry is, just sort of abstractly. A positive geometry is just a compact region in some space, but with the property that it has boundaries of all codimension. So it has its interior, it has a boundary of codimension 1, codimension 2, and so on. So it's a real geometry. So the easiest picture to have in mind is the inside of a triangle or a polygon, or higher dimensional polyhedra and polytopes. I've drawn it sort of potentially curvy here because in the applications for n equals 4 superdiagonals that I won't talk about, they can also be curvy. So that's a little irony of the story, is that we actually ran into a more geometrically sophisticated version of these ideas first. But so you can keep in mind the inside of a polygon, for example. But so on the one hand, we have a geometric region, but on the other hand, there's an analytic object associated with it. There's a unique differential form known as the canonical form. There's a unique differential form that has a property that it has logarithmic singularities on and only on the boundaries of P. So logarithmic singularities are just singularities that I can't get rid of by rational, that are singularities that I can't get rid of by rational transformation. So they locally, there's a choice of coordinates, so they look like dx1 over x1 up to dxd over xd. So d log x1 wedge up to d log xd. So there's a real geometry here. And then there's a complex form, which is totally determined by the geometry. It's determined by having singularities on, logarithmic singularities on and only on the boundaries of the space. So as we'll see, these forms are going to be what are associated directly with the amplitudes. So we're going to be thinking about the scattering of amplitudes is really secretly a differential form that lives on kinematic space. And what determines the differential form is the existence of this real geometry, and asking for this form to be the canonical form of that of the corresponding positive geometry. Anyway, here's some very simple examples of what a positive geometry is. So I can have the inside of an interval, for example, between A and B. And here, the form would just be dx over x minus A minus dx over x minus B. Okay, and you see the minus sign is important. If I had a plus sign there, it would have logarithmic singularities at A and B, but it would also have a logarithmic singularity at infinity. So the point is that the positive geometry should have, that the form should have singularities on and only on the boundaries of the geometry. Similarly, if I go to the case of a triangle, the canonical form is just dx dy over the product of the linear factors defining the triangle. And again, you can check that now if I take a residue, let's say where x equals 0, so that would put me on this line, that the resulting form, which would just be dy over y times 1 minus y, has logarithmic singularities again at this point and at that point and nowhere else. So this is an important point, is it has logarithmic singularities on and only on all the boundaries as you go all the way down to points in the end. So it's not just the codimension 1 boundaries. That's the sense in which the geometry sort of completely determines this interesting form. So if I move on, already the case of a quadrilateral or a pentagon is more interesting, because if you only care about the codimension 1 boundaries, you'd put the, let's say for the quadrilateral, the 4 linear factors downstairs here, then it turns out that generically the form would have singularities elsewhere. It could have singularities at these illegal points that are not part of the geometry. And so you need an interesting numerator to put a 0 there in order to make sure that the form has singularities, again, on and only on the boundaries of the quadrilateral. And it gets more interesting as you go up to pentagons and higher. Okay, so already the case of 2-dimensional positive geometries that just polygons is rather interesting. But here we see one first basic point, which is that singularities of this form correspond to boundaries or facets of the positive geometry. Okay, so that's a point we'll be coming back to again and again. And in fact, we're going to be basically transitioning to think about the geometry all the time, but we know the singularities of amplitudes are important, and that's going to be reflected in the boundary structure of the positive geometries. Another general point is, let's say you want to compute these canonical forms. There are many ways that we've learned to compute them over the years, but one of the most obvious ones is via triangulation. So let's say you have a sort of more complicated positive geometry like this hexagon. Well, if you can tile this positive geometry by simpler ones like these triangles, then it's very natural, not 100% trivial, but anyway, it's true that the canonical form for the whole polygon is the sum over the canonical forms for each one of the triangles. And as we saw, the canonical forms of triangles are simple. Now, so they're known. Now, you see that each one of these guys is going to have a pole. For example, omega p1 will have a pole on this middle line there, which is not a legal pole of the whole geometry, but that pole cancels between p1 and p2. And it can do that precisely because when I go on this line, when I take a residue to end up on that line, the canonical form only knows about this line. It doesn't know about where it came from. It doesn't know whether it came from P1 or from P2. So precisely the sort of recursive property of canonical forms that makes it possible that the sum over the forms of the triangulations gives me the form for the whole answer. Gives me the form for the whole geometry. I'll mention one specific class of triangulations of polytopes because later we'll see that these will be known as Feynman diagrams. If you have polytopes that have the property of being, the so-called property of being simple, that means in the neighborhood of every vertex, they locally look like a simplex. So that's true for all polygons, for example. Then here's one triangulation that also gives you the canonical form, which is you just go to every vertex. You go to every vertex of the positive geometry, and then you wedge together the d log of all of the equations, of all the linear equations defining the faces that meet at that vertex. So I've drawn the example here for the case of a square, and you see this corresponds to a particular funny triangulation of a square where I add some artificial line, let's say at infinity. I can put it wherever I want. And then I just draw triangles out from every vertex. So here's one, here's another one. Every vertex, I draw a triangle. And you see that I can get an inclusion-exclusion type triangulation that gives me this square. This big triangle minus this triangle minus that triangle plus this triangle gives me back the whole square. And that triangulation of the square gives me this formula for the canonical form. So that's one very particular way of getting the canonical form for one very particular class of polytopes. Okay, maybe I can stop at this point and ask if there are any questions. I saw some questions came up on the chat, so let me just pause for a second. Okay, all right, sorry, there were no questions.
That was just me asking about who's doing it in India. Sorry, go ahead.
No problem. Yeah. Okay. Let me continue then. Okay.
Sorry,
let's talk about.
Sorry, I had a question.
Is there another question?
Yeah.
Yes.
You just showed this this peculiar triangulation of a square. Is there? Do you know why one needs to look at such a triangulation? You haven't.
What you don't? There are many triangulations. And we'll talk about other ones. In fact, as we'll see when we talk about associahedra and clusterhedra, these triangulations are the things you can interpret as Feynman diagrams. And in fact, the very fact that they force you to add this artificial line at infinity is what obscures a symmetry that the answer has. So even this dumb phi cube theory has a symmetry. A hidden symmetry. It's the analog of the dual conformal invariance of n equals 4 super A mills. We'll talk about it in a moment. But it has a symmetry that's hidden by Feynman diagrams precisely because they do this dumb thing of adding this plane at infinity. This triangulation is not as peculiar as it might appear at first once you're in this game a little bit. But let me give you a quick picture for why it's not that peculiar. Here's a totally obvious triangulation. Let's say you have this polygon, you put a point in the middle and you draw lines out to the vertices. That's the kind of pizza slice triangulation. That's a completely trivial triangulation. Any idiot would think of that one, right? Well, if you take a polygon, one sort of beautiful fact is that if you triangulate a polytope, you can triangulate it by either triangulating the polytope or triangulating the dual of the polytope, where the dual is in the usual sense of interchanging points and lines in 2 dimensions, or points and planes in general. So if you imagine what the dual of this dumbest pizza slice triangulation looks like, it's exactly what we just drew, right? Instead of putting a point in the middle of the polygon, in the dual, the point turns into a line. So you put a line outside the polygon, but then you're doing exactly the same thing. So this triangulation that corresponds to Feynman diagrams is really the dual of the dumbest triangulation that you might have.
I see.
Hi, could I ask a couple of questions, please, quick ones?
Sure.
I had 2 questions. The first is, they may be naive at the very outset. I apologize in advance. So the first question is, when you talk about these canonical forms, the so-called omega, it is so tantalizingly suggestive of the Griffiths form in algebraic geometry. And so what I was wondering was, is there an analog of the Picard-Fuchs equation, which could be essentially, is there a differential equation which is satisfied by this form, which you could solve and not care about the integral? In other words, you don't care to solve the integral, you solve the equation, you get the omegas, you can construct an analog of period vectors.
Question. I would love to come back to this question at the end, if you don't mind.
Okay.
So this is there's a lot to say about this question, and I should have said that I'll be giving maybe 8 or 9 hours of lectures on this subject in 2 weeks at the ICTS. And essentially, the question you're asking will be the theme of one of those lectures.
Oh, cool, cool, very cool. Okay,
yeah.
can I just ask my second question in case if it's okay?
Yes, please.
Yeah. Okay. So from what I recall of this paper of Witten, I guess 2003. I think there was a map of calculations. If you go from some kind of a transform to the twistor variables,
yes.
So the calculation could be mapped to essentially an instanton sum in a topological string theory in a supermanifold. So is there some version of that could be carried out for this?
I mean, so I can also come back to this question later. The twistor string was important in many ways to sort of show that there was some potentially deep mathematical structure associated with amplitudes. But in a sense, all of those things have been subsumed long ago in this business and understood much more simply. Okay. So, but that's a kind of almost a 10-year-old story now. Okay. That the entire connection between n equals 4 amplitude and the grassmannian explained essentially everything. Many of those things that and so all of the fancy schmancy infinton topological Bima, all that stuff there's a much simpler, sort of deeper structure that explains that, and also the connection to many other things. So
okay, thank you.
So but I will take this opportunity to say that a point that we'll come to again in a second, that almost every approach to amplitudes invokes some auxiliary space. So you do a calculation in some auxiliary space, and then you interpret the answer as telling you about an amplitude that doesn't see that auxiliary space. The most obvious one is Feynman diagrams, which the auxiliary space is the interior of the space-time that you don't see in the final answer. In string theory, good old-fashioned string theory, it's the string world sheet where you do some calculation on the string world sheet in order to get an answer that you interpret as a space-time scattering amplitude. In the twistor string, similarly, there's a twistor string world sheet. You do a calculation there. In the story of the amplituhedron, there was some auxiliary grassmannian space where you did the calculation. The new thing that's happened in the past couple of years, and we'll see an example now, is that the questions are being asked directly in the kinematical space. No auxiliary spaces are involved. Directly the kinematical space in order to get the answer, and that's a novelty that's going to drive some of the things that I'm talking about.
Okay.
Any other questions?
Yeah. This extra line at infinity that you put, can it be thought of as a kind of a completion of the algebraic variety whose period you are going to calculate? Probably will.
No. No, it's not. And in fact, I should stress that with these forms that I'm talking about at the moment, we're not going to be integrating them. I'm going to tell you how to interpret the amplitude, how to get the amplitude from them, but it's not that we're going to integrate them.
So it's not like adding a divisor or something.
No, it's not. No, it's really arbitrary. It's an arbitrary point that we're adding. It's like as arbitrary as the point you put in the middle of the pizza slice in order to make a triangulation. Totally arbitrary.
Thank you.
Okay. Any other questions? All right, great. Then I'll proceed. So let's talk about the theory that we'll be talking about. We're going to be talking about this bi-adjoint phi cube theory, and really this is just an excuse to look at the same old planar, the same old diagrams we draw in large N theories. It's not going to be planar, as we'll see. This is we can do this on in any order in the one of N expansion, but it's the diagrammatics of Yang-Mills theory, except we want to have an excuse to do it with a very simple theory with only scalars, so no complicated polarization vectors or anything like that. And so in order to do that, you can't write down the interaction FABC, phi A, phi B, phi C, because that would vanish by the antisymmetry of FABC. So you give it two colors, so F little ABC and F big ABC. But then the amplitudes in this theory have a trace decomposition, as we're always used to, except there are two traces. So you can call the quote-unquote single trace terms would just be a single trace for one color and another single trace for the other color. The double trace terms would be beyond tree level. We'd have two traces on one side and two traces on the other side, and so on. And so the diagrams for this theory have the usual 1/n genus expansion, where if you choose some color ordering for the little a's and some big A's, all the diagrams that you draw have to be compatible with both of the orderings. And so what we're going to do is just imagine the orderings on one side on little a's are the same as the orderings for the big A's, so that means that we just simply include all the diagrams. So again, the diagrammatics is identical to the usual diagrammatics of large N Yang-Mills or any other single adjoint large N theory. All right, so what do we have at tree level? At tree level, we just choose some ordering for the external particles. Sorry, I should have written it. There's some ordering like 1, 2, 3, 4, 5, 6 here. And then we just draw all cubic diagrams that are planar with that ordering. Okay, so that's what the Feynman diagrams are. Now, it's going to be very convenient for us to think in terms of the duals of these Feynman diagrams instead. So instead of looking at this plain cubic graph, we're going to draw its dual. And you'll see that the dual of this graph gives me a hexagon and actually gives me a triangulation of the hexagon. Okay, so now these dual graphs are also useful because they naturally give us a basis for all the kinematical invariants of this problem. So if you give me all the momenta of the particles, again, there's an ordering P1 through Pn, so it's natural to put them end to end on a d-dimensional piece of paper. They'll give you a closed polygon. And so it's natural to talk about the distance squared between 2 points on this polygon that are the sum of a bunch of consecutive momenta, pi up to pj minus 1 squared. So I'm going to be calling those variables xij. You see xij is the same as xji. xii plus 1 is 0, because I'm imagining these particles are massless. Actually, we could imagine they have any fixed mass. It doesn't make any difference, but just for convenience, I'll call them massless for now. And a very nice thing about these x's, so these chords of the polygon, are exactly enough of them to give me a basis for all the independent Mandelstam invariants for this scattering process for endpoints. Very simple to see. The counting is exactly correct to give you a basis. So these variables are precisely the things that show up in the propagators of cubic diagrams, and they're also a basis for all the variables. And so in this language, the tree amplitude is just the sum over all the triangulations of the polygon. And for each triangulation, the product of all of the chords in the triangulation of 1 over the x for that chord. Okay. All right, let me go back to full screen mode here. Okay. Now, already in this very simple example at tree level, we can see how locality and unitarity are sort of imprinted in these very simple objects. Locality is what tells us the kinds of poles we're allowed to see together. So we just discussed that we're allowed to see these only what looks like triangulations of the polygon, and we can't see crossing chords. So seeing crossing chords is like seeing a singularity in the S and the T channel at the same time. We can't have that. That's not compatible. Doesn't go along with a local picture in space-time. Okay, on the other hand, unitarity is simply the statement as one of these variables, one of these chord variables goes to 0, the amplitude factorizes into the product of two smaller amplitudes associated with the smaller polygons. Okay, and so now, now I want to sort of back up, heading towards the sort of question of what kind of, so now we're beginning to see again slightly more sharply the question. Our kinematic space is just these xij's. That's it. Those are the obvious kinematical invariants. Our kinematical space are these xij's. And now in the space of xij's, we want to learn to ask a question whose answer is this tree amplitude. If we didn't know about diagrams or triangulations or anything, what kind of question would give us this answer? So for the next few minutes, I want to pretend that I'm an experimentalist who doesn't know any of these things, and all they do is move around these x variables and see what happens. And of course, the first thing they would notice is that as you move these variables around, the amplitude blows up. So they would notice that the amplitude has poles. And so clearly, that's a big clue to what's going on. So they're going to study what happens in the neighborhood of these poles. And one kind of experimentalist who's really a closet theorist will see that they'll do very detailed measurements and see that in the neighborhood of the pole, the amplitude actually factorizes into the product of two lower amplitudes. They'll be very excited about that. And they go announce this amazing experimental observation at a conference. And in this conference are two theorists. One of them is named Feynman and says, oh, this is a big clue for what's going on. I know what's going on. It's Feynman diagrams that I just named after me. I'm just summing over all of these things now with virtual particles on the inside, but this picture guarantees where the poles are and it guarantees factorization of the poles. And there's another theorist in the audience whose name is Deline, and he says, no, that's not what's going on. I've seen this before 100 times. This is what happens in the simplest moduli space. The first thing you ever study in Geometry 101, the space of endpoints on the boundary of a disk, endpoints on P1, and that space has the property that as you go to its boundaries, it has this bubbling picture. It factorizes into two other spaces of exactly the same type. And that's the clue for what's going on. And you see, this is to highlight that if factorization is the star of the show, then what we get from that are either the particles in space-time picture for what where these scattering amplitudes come from, or the string worldsheet picture. So in both cases, there's a sort of primitive underlying structure that has this factorization on its boundary that has this factorization structure for its boundaries that we then slightly decorate with a dictionary to turn them into these functions that have these properties that we interpret as the amplitudes. Okay, but the hero of this little story of mine is someone else. Is a lazier but smarter experimentalist so I mean, you can ask what is it that remains to be desired? Is there anything left to be desired in this picture? And this lazier experimentalist actually does a different kind of measurement. Instead of doing anything very detailed in the neighborhood of the poles, they just get excited by the fact that they can get the amplitude to blow up. So having made them blow up, they just want to make it blow up more. So they move the other kinematic invariants around and they see if they can get single poles, double poles, triple poles, what they can get. And they observe that there's an interesting pattern in how the poles can come together. For example, for n equals 4, you can have poles in the S channel or the T channel, but not both of them at the same time. For n equals 5, I can have a pole when, let's say, P1 plus P2 squared goes to 0, and then when P1 plus P2 plus P3 squared goes to 0 as well, and the cyclic rotations of this, but no other combinations. So there's an interesting pattern in how the poles come together, and this experimentalist might want to even graphically denote what that pattern looks like. And it's slightly cool, even for the case of 5 particles, that you can denote this pattern by a picture. So here's the picture. It completely coincidentally looks like a pentagon. But the picture is that you want to imagine the kind of interior of this space is no poles at all. You want to imagine the edges are where you have single poles, and the vertices are where you have double poles. So I end up, for example, on this factorization channel in the bottom, and from here I can go to two further factorizations where I get a double pole, where I take this 4 point and I blow up in two different ways, on one side and on the other. And you see, it's slightly non-trivial that all of these factorizations, the single and the double, can actually fit together and be geometrically represented as the edges and vertices of this pentagon. For the case of 4 particles, it's even simpler. It would just be an interval. The inside is just the full amplitude. On one side, I have the S channel, and on the other side, I have the T channel. And it takes a lot more imagination to see if this can keep working. But if I, sorry, and here I'm drawing exactly the same picture in the language of triangulations of the corresponding polytopes. But this ends up being true for any number of points. So if we go to n equals 6, there are 3 poles that I can have. So if the picture works, you should be able to draw a 3-dimensional picture. And the mathematician Jim Stashev in the 1960s figured out that this was true, that there is indeed, in this case, there is a 3-dimensional picture where the vertices can be thought of as triangulations. The vertices can be thought of as the cubic diagrams, and then 2 vertices are connected by an edge if there's a partial factorization that connects them, as we see in this picture, or in the language of triangulations, a partial triangulation that contains. In fact, Stashev himself did not realize that you could literally draw the picture as a polytope, the way I've drawn it here, with flat edges, with flat faces. And it wasn't until the 1980s till people realized that you could actually realize these objects as honest polytopes. Okay, so this is a qualitative fact. It's not an obvious fact. It's a qualitative property of the pattern in which the poles can come together, that they can be represented as the facets of a polytope. And I want to stress that neither the particle nor the string picture make this qualitative fact obvious. So this is some interesting kind of fundamental fact about something very simple and universal, the pole structure of amplitudes, which is not seen by those pictures. But on the other hand, this picture of this so-called associahedron does make it obvious that you have factorization. Or it's seen in the structure of the associahedron, because when you go to the boundary of the associahedron, so if you want to see what the poles look like, you go to the boundaries of this space. When you go to the boundaries, every facet of the associahedron is in fact the direct product of 2 lower associahedrons. Okay, so for instance, if I draw a picture here, here I've drawn the same thing now in terms of triangulation of a hexagon, and here's a partial triangulation for this edge, and an even coarser triangulation for that face. You'll notice that this picture has 6 faces that look like pentagons, 3 faces that look like squares. The pentagon we already saw was the picture we get for a 5-particle scattering. And so all of these 6 faces are exactly the 5-particle, 3-particle factorization on one side, whereas the square is the 4-particle, 4-particle factorization, because remember, the 4-particle is an interval. So from here we get an interval, cross, and interval. Okay, so now we're beginning to, again, further sharpen our question. Our kinematic space is just xij's. How can we make it obvious? What kind of question can we ask in this kinematic space that makes it obvious that there's a polytopal structure and that it factorizes on its boundaries? So this is some kind of qualitative clue to the sort of theory that we're looking for in kinematic space. All right, now here's one more fact, which is less, I mean, that's a sort of striking qualitative fact. Here's a simple, more quantitative fact, that in fact these amplitudes for this 5-cube theory have a hidden symmetry. So let me explain to you what this hidden symmetry is. In order to see this hidden symmetry very clearly, we actually have to upgrade our thinking about the amplitude from a function to a form. So here is a simple example at 4 points. We would normally think of this as 1 over s plus 1 over t, or maybe 1 over x13 plus 1 over x24 in the language of these new variables that I talked about. But I'm going to upgrade this to a certain one form instead. So instead of 1 over s, I'm going to write ds over s. Instead of 1 over t, dt over t. And now comes the important point that I have to actually add them with a minus sign. Now, why do I have the minus sign? Well, one natural thing to want for this object is that it shouldn't depend on the overall scale, the units of s and t. It should only be a function of the ratios of s and t. So that means that it should be well defined on the projective space of s and t up to overall rescaling. And with a minus sign, this is indeed d log of the ratio of s over t. With a plus sign, it would not be. Now, in this case, there was just one thing I had to check, and there was one sign, so it seems trivial. But beyond 4 points, the invariance of this form under this projective rescaling is actually a highly non-trivial condition, and it ends up imposing many, many more equations than there are unknowns on these signs. So just by counting equations and unknowns, it's not remotely obvious that it's possible. And yet it is possible. So in this extremely overdetermined system, it's possible to choose signs so that this form is projectively invariant. And again, so this is an interesting hidden symmetry of this of the amplitudes in this simple scalar theory. That's a very precise analog. I don't really have time to explain what I mean by this in detail, but it's really an analog of the dual conformal invariance of n equals 4 super Yang mills. So that's one interesting fact. When I upgrade the amplitude to a form, the signs can be chosen so that it's projectively invariant. Another interesting fact is that I can actually naturally recover the actual function of the amplitude from the form. And I can recover it in the following way, that this form is defined on the ST space, or x13, x24 space, let's say in the simple 4-particle example. The space is 2-dimensional, even though the form is a 1 form. So if I want to get a function out of the 1 form, somehow I have to find a natural subspace to pull this form back onto a 1-dimensional subspace. And here's a natural 1-dimensional subspace. x13 plus x24 equals a constant. So I've drawn it just as this line here. And you see, if you pull back this form on that subspace, then I just get the volume form on the subspace, for example, dx13. The minus sign goes away, and I just get 1 over x13 plus 1 over x24, which is the amplitude. Again, at 4 particles, this looks a little trivial, but at higher end, this is non-trivial, that it's possible to find a subspace to pull this back onto, such that when you do, you just pull out an overall volume form multiplied by the amplitude. But it is possible, and we'll be talking about where that comes from in a little bit. Okay. So finally, around 2 years ago, with some friends, we did run into this polytopal structure in kinematic space. We did run into the associahedron from sort of physics motivations, sort of physics guesswork. We ran into an interesting, actually new realization of the associahedron as a polytope. This is what it looks like for the case of 6-particle scattering. You might notice that this sort of combinatorially looks like the previous shapes that we saw, like that one, but it's a very specific version of it. It has all these parallel sides. It's a very particular realization of the associahedron. And quickly it was realized by some of our mathematician friends that this way of thinking about the associahedron was closely related to cluster algebras, and in fact gave a conceptually transparent way of understanding certain polytopes, generalizations of the associahedron that are associated with cluster algebras more general. So I don't have all that much time left, so I think I'll probably sketch a little bit how these things are related to cluster algebras in the rest of the talk. But for most of the rest of the talk, I will really assume you know nothing about cluster algebras at all, and try to say things in a simpler way that doesn't rely on that knowledge. Eventually, it's really crucial to understand how these things are related to each other, and I will be talking about that and the entire connection to the cluster structure very systematically in the lectures that I alluded to that I'll be giving at the ICTS in a couple of weeks. But anyway, this is another version of the same question now in kinematic space. What kind of question can we ask that makes it obvious that we get this kind of fancy associahedron structure? So again, all of these are clues to the theory that we're looking for in kinematic space. Okay, maybe I can stop here because we're now going to transition. We're not gonna in a sense, you can forget everything I've said, and the next little while is totally self-contained by itself. So maybe this is a good time to stop and see if there are any other questions. Were there any questions?
Nima, were you talking? Was your discussion restricted to tree diagrams too? Also,
in this motivation so far, it's tree diagrams. The general story of cluster in the motivation so far is tree diagrams. You know, as of last December, we understood how this connection to these so-called finite-type cluster algebras pushes things forward to one loop. And what we're working on now with these clusterhedra is all loop order and all orders in 1/n, which involves many new ideas, but and are not these cluster polytopes. You know, we had a new description of them and a new realization of them, but for finite-type cluster algebras, they sort of existed already. There's a number of new things that have to happen when you go beyond that, which were not sort of obviously known in the cluster world either, but that's what we're working on now. And it seems to, I mean, you know, we're in the middle of it, but we can already do lots of non-planar things, 2 or 3 infinite loops for many classes of examples. So, yeah, we think this has nothing to do with, certainly nothing to do with tree level, nothing to do with planarity. It's something, there's a known kind of deep structure associated with Riemann surfaces and cluster algebras, and it's being studied by the cluster algebra. This is not a done subject. You know, cluster algebra is a very active area of research, even in mathematics, and there are some very puzzling and fascinating things about them when we go beyond these simplest finite type cases. So that's really what, you know, if I got to the actual clusterhedra in this talk, that's mostly what we'd be talking about, is Riemann surfaces and the mapping class group and all sorts of puzzling infinities that you have to learn to deal with. But it seems like we can do it. So
can I ask a question, Nima?
Yes.
I have a question. It's a see, in usual physics, we differentiate between different types of theories in terms of degrees of freedom and a Lagrangian.
Sure. Right.
And it has various properties. Here in this formulation of yours, how do you distinguish between different types of theories? I mean,
yeah, excellent question. I mean, so we have there's a couple of different sort of answers that you could have, but let me maybe jump to the sort of deepest one. The theories like n=4 and phi cubed theory have the property that all of their that in a sense that something makes them unique, because 3 particle amplitudes are unique, are just specified by Poincare invariance. They have the property that once you specify them, everything else sort of comes along for the ride and is controlled by sort of long distance factorization behavior. Anyway, that's so roughly what's going on is that in all these cases of positive geometry, you can sort of summarize the story by saying there is an extremely intricate sort of pattern of what kind of singularities you can have at long distances that we normally think of as some complicated output of field theory, but you can actually think of as the ab initio starting point, the answer to some other question, some sort of one-line mathematical question actually forces all of that structure on you. And then you look for this form of logarithmic singularities that sort of uniquely determines the object, right? Now, what happens in more general theories, for example, if I have 4-point interactions, then you have to say a lot more. You have to say what 4-point interaction. Is it dimensionless? Is it, you know, s² + t² + u²? What is it, right? And that's, I think, that's an area that's really just starting to be explored, because it's totally obvious that there's still geometries associated with it. The work on one direction is the work that I alluded to on Stokes polytopes and accordiahedra and so on, to find a different kind of positive geometry associated with the different theories. It even lets you talk about all, adding many different kinds of interactions together. That's sort of one direction. Another direction is that clearly we have to go beyond the idea of just logarithmic singularities. So, in other words, when you have interesting numerators, then we have to go beyond just the idea of log singularities and somehow enrich the way in which we can tie forms to a geometry. But yeah, that's sort of, generally speaking, work that's pretty much in its infancy. But I should say that it's totally clear that many of these things are just sitting there waiting to be discovered and explored. For example, going all the way back sort of 8-9 years to the story connecting n=4 amplitudes and the Grassmannian and the positive Grassmannian. Already back then, you could go to non-superysmmetric series. All the structure was exactly the same, except that in addition to the things that you could associate with this geometry of the positive Grassmannian, there was another place in the Grassmannian where there was infinity in momentum. So I would say that the kind of big novelty that's missing in this subject is to understand what's going on at infinity. We've understood in the ultraviolet. So in a sense, we're seeing more and more examples of how positive geometries encode all of infrared physics, factorization, soft things, and so on. But understanding some analog of the geometry for the ultraviolet is a big open problem. But I mean, starting to be explored.
Okay,
did that answer your question, Spenta?
Yes, I think, thank you.
Okay.
Right. Nima, one more quick question,
Yeah.
please. You talked about encoding the momentum data. Can that be generalized to polarizations as well?
Another wonderful question. So one of the I told you today I'm just talking about these phi cube theories, but all of this kind of morally grew out of the story of the amplituhedron. In the story of the amplituhedron, the structure of our kinematic spaces is different. In the story of the amplituhedron, the kinematic space is literally the space of the n null momenta for the external particles. Okay. Now, thought of slightly more nicely. So if you talk about the sort of original so-called momentum twister amplituhedron, instead of literally null momenta, there are these momentum twister variables, but they're very simply related to the momenta. I mean, algebraically related to the momenta. There's a so-called momentum space amplituhedron, which is just the space of the spinor helicity variables for the external data. There, what the form is doing is precisely letting you keep track of the helicity information for the particles. So that's kind of a cool thing, that instead of using polarization vectors, or even using SUSY on-shell Grassmann variables, which are the two ways we're used to keeping track of polarization data, in fact, this differential form keeps track of the polarization data. One way of saying it is that if you have a negative helicity gluon and a positive helicity gluon, we normally don't know how to add the amplitudes for them, but I can add them if I take the negative helicity one and I turn into a form by wedging with d squared lambda tilde for it. That eats up the weights, and I can do the analogous thing for the positive helicity guy. So you can even do this in the standard model. I mean, we can talk about the amplitudes as differential forms in the standard model, and these differential forms keep track of all the helicity information. That's exactly what happens in the case of the amplituhedron. Our kinematic space is just the space of the external momenta, or spinor helicity variables, or momentum twister variables, and the form, the components of the form unify all the different helicity amplitudes together. In the story of the bi-adjoint theory, the kinematic space is quite different. I mean, it's also natural for a scalar theory, but it's the space of the Mandelstam invariants. And if I had longer, I would tell you that the purpose in life of this differential form, the analog of it keeping track of helicities, is actually keeping track of color. But anyway, I don't have time to explain that more right now. I'm happy to do it later. But the answer to your question is that a quite different treatment of the kinematic space is what's going on in the story of the amplituhedra, and there it does keep track of helicity. I think if you want to keep playing with the idea of polarization vectors instead of what we normally do, at least in 4 dimensions, to go to these more invariant ways of talking about things with spin helicity variables, then this is connected to my answer to Spencer's question. We need to somehow enrich the notion of these geometries in some way that allows non-trivial numerator factors. So things that aren't just like d-log forms, but have some more information associated with them. And there's lots of sort of circumstantial evidence that there's something like that exists, but trying to do it precisely is not understood yet. Did that answer your question, Charles?
Yes, yes. Thank you.
Great. All right. Now I think I'm at about time. So if you guys don't mind, maybe can I just just say one more story, just so you have. I think I've brought it to a point where. Can I maybe have 15 minutes? 15 more minutes?
Yeah, sure.
Okay. All right. Okay. As I said, so I think I'm really not going to get to the all loop, all orders in 1 over n type ideas, the really new Clusterhedra ideas. But those of you who are really interested, if you come to at least the later part of the lectures on July 24th, I think I'll be talking about the subject completely systematically from the bottom up, if you're interested. Okay, so let's okay. So forget everything. I want you to forget absolutely everything. We have just set up the question. Okay, so that's a long motivation, but now I want to start answering it. I want to start giving you a picture for what kind of question we can ask in this kinematic space that's going to give us all these wonderful structures out. And again, what is our kinematic space? Just the space of xij. So what the heck are you supposed to do in the space of xij? You just have these stupid labels I and j. What can you do in this space that's going to give us all this structure out? Okay, well, we're actually going to see that despite its seemingly boring appearance, this space actually has a space-time structure. It has naturally a causal structure on it. So this kinematic space naturally has a causal structure associated with it, and that will let us ask certain quote-unquote dynamical questions in this space, and that will lead us to all the objects that we're seeing before. Okay, so what is this funny causal structure? Well, to begin with, I'm just going to write all of the variables down. I'm just going to draw them on a sheet of paper. Okay, so and of course it's natural because I have this cyclic structure. It's natural to start with any one of the variables, let's say x15, and just start from that guy and translate the indices, either the I index or the j index, just by cyclic rotation. So this is just a highfalutin way of saying that I can just put these variables on a grid in the most obvious way. 1, 3, 1, 4, 1, 5, 1, 6, 2, 4, 2, 5, 2, 6, 2, 7, and so on. This is the case of n equals 7. But there is something interesting that, remember, 1, 2, the edges of the polygon are null, so those are 0. That I've drawn in black. So that would be 1, 2 is 0, but then 1, 3, 1, 4, 1, 5, 1, 6, and then 1, 7 is 0 here again. Because of those zeros, this space has a natural boundary, and I've drawn it vertically. I mean, I could draw, if I drew the grid in the dumbest way that you would draw it, like in the horizontal and vertical directions, the grid would, the boundary line would go off at 45 degrees. So I'm just tilting it so the boundary line is vertical. Okay, so that's my space. You'll notice that there's an interesting Mobius structure on this space. If I sort of just label it in the continuum for a second, I'm going to call this direction t and this direction x. The reason for calling it t will become apparent in a second, but just again, a sort of a trivial thing is that, remember, ij and ji are supposed to be identified with each other, and so here, if I have x and t, then up there, ji is 1 minus x and 1 plus t. So I have this infinite band with this Mobius identification on. But now comes the interesting point. Where is this sort of causal structure coming from? And that's just this very, very basic fact. What are we doing in this picture? We begin just with the chords on the polygon. And now every chord on the polygon is being represented as a point in this kinematic space. But we've already seen that it's important whether chords cross or not. So let's ask, if I have two chords, ij and kl, what does it mean if they cross? Well, what it means if they cross in the polygon is the following very simple but beautiful thing in the space. If the chords ij and kl cross, that means that I can think of ij and kl as the past and future corners of a causal diamond that fits in this space-time, if you think about t as time and x as space. So in other words, there's a causal diamond where the past and future corners are ij and kl, the left and right corners are ik and lj. Okay, and so that's what it means if chords cross. If the chords don't cross, it either means that these points are space-like separated, or that they're time-like separated, but so far apart in time that the light cones from the top and the bottom can't actually intersect each other. So the causal diamond does not fit in the space-time. So that's a very early hint that there's something, that there's some causal structure. There's a kind of a dynamical question that we can ask in this seemingly boring kinematic space. Okay, so just a little bit more about the kinematic space. If I just want to cover all of the ij or ji variables just once and only once, then I have to take a chunk out of this kinematic space. For example, I can't take the whole thing, obviously, because I would double count. So here's 1, 3, for example, and then there's 3, 1 up there. I don't want to include both 1, 3 and 3, 1 in my variables. So that's a chunk out of this space-time, and there are many ways of doing it. Here's one of them, which I'll be focusing on for the next little bit, just for simplicity. Okay, so we have to take a chunk out of this kinematic space-time. All right, now we have to ask a question in this kinematic space-time, and the question that we're going to ask is just solving the wave equation. Okay, so just the sort of simplest thing you could imagine. So I'm going to switch to light cone variables, u and v, and so we're looking at du dv x equals c. And there's only two things about the wave equation in 1+1 dimensions that I want to remind you of. One of them is that there's a lovely Gauss's law, sort of integral version of the wave equation in 1+1 dimensions that just tells me that if I take any causal diamond in the space-time, that the value of the past plus future minus left minus right is equal to the total charge inside the diamond. Okay, so that's the integral form. Obviously, if you shrink the diamond to 0 size, that just recovers the wave equation for you. Another fact that we'll use just at one point, very simple fact, is that if you have a solution of the wave equation, and you have some 45-degree band region here, and you don't care about what's going on in that band, then you can make another solution of the wave equation simply by scrunching that region away, just keeping it still x right and x left on one side or the other, and whatever source you had inside here, you can replace by a delta function at the juncture between the two. And this fact is obvious simply because any Gauss's law box that you would draw in this bigger picture would give you exactly the same answer as in this smaller one, provided you include whatever charge you had in there as a delta function. All right, so we're going to be looking at solutions of the wave equation, but in previous experience with this story where we looked for structure in kinematic space, especially that we saw in the amplituhedron, we also saw that you have to say the word positive. And so we're going to be looking at positive solutions of the wave equation. So in other words, we're going to be solving du dv x equals c in one of these chunks of the space-time, like the one that I talked about before. Remember, positivity means something because we already saw that we have 0 on one boundary and on the other. So when I say positive, I mean bigger than that 0. And I'm going to ask for the source to be positive. Okay, so that's it. So we're going to, in this kinematic space, we're going to look for positive solutions of the wave equation. Okay. Now, that question turns out to have a remarkable answer. So let me be more precise. It's very simple to see that if you just give me the data, let's say on this past surface, then using the Gauss's law, that suffices to determine all of the x's everywhere inside the diamond, together with these boundary conditions. Okay, so just giving data on this past here fixes x everywhere inside, and therefore asking x to be positive everywhere inside puts some restrictions on some kind of positivity restriction on what x can look like, let's say on this past surface. Okay, so we're trying to figure that out. We're trying to figure out what restrictions do I put on this past surface in order to guarantee that x stays positive everywhere inside. And that problem seems pretty hard because there's a sort of continuous infinity here of functions on this past slice. But let's ask a simplified version of the question. Let's ask what can I know about the values, let's say here at 3 points on the boundary. Then I can do 4 or 5, any number of points, but for any fixed number of points on the past boundary, I'm going to get some kind of slicing of the data at those points. And how do I find what it is? Well, I take all of those points, I draw the obvious light cones that emanate out of them and fill out the rest of the space-time like this. And then you can easily see that using so obviously the value at 1, 3, 1, 4, and 1, 5 has got to be positive. But you can use the Gauss's law to also compute 2, 4, 2, 5, 3, 5, 2, 6, 3, 6, 4, 6. You can compute all of these points in terms of the values at 1, 3, 1, 4, and 1, 5 linearly, as well as whatever the total charges are inside all of these little meshes. And so if you then demand that everything on the inside is positive, you're going to put further linear inequalities on the space of 1, 3, 1, 4, and 1, 5. So to begin with, of course, 1, 1, 4, and 1, 5 have got to be positive, so you have some positive orphans. But then you have further positivity conditions that come from demanding that everything else on the inside is positive. Now, remarkably, it turns out that this question forces the x's on 1, 3, 1, 4, and 1, 5 to precisely lie inside the associahedra. And in fact, not a random realization, but precisely this ABHY realization of the associahedron that we ran into from sort of physics guesswork a little over 2 years ago. Okay, so asking for positive solutions of the wave equation gives us the associahedron, and you can just sort of observe that, but just by doing the calculation. But the conceptual reason for it, and this is the most interesting thing, is that this picture of the positive solution of the wave equation in kinematic space makes it obvious that we're looking for a polytopal region, but it also makes it obvious that this region factorizes on its boundaries. So this is what I advertised earlier on. You know, Feynman diagrams in the string worldsheet make factorization obvious, but they don't make the polytopal realization obvious. What we're looking for is a picture that makes it obvious that we have a polytope that also factorizes on its boundaries to the product of two smaller polytopes of the same type. And this picture that I'm just referring to is exactly the one which does that. Let's see why. How do we understand factorization? Well, let's imagine that we're trying to go to a boundary of this space. We're asking for x to be positive everywhere. So as I move the values on the boundary around, I want to make sure that x is positive everywhere. When I move the values on this past surface around, I want to make sure x is positive everywhere. But a boundary of the space would be one where somewhere on the inside, x goes to 0. So let's say at this point star, x star goes to 0. And now it's natural to ask where else I can put x to 0 after I've put it to 0 here. And if you just draw the light cones out from this point, then everywhere in the red here, it's very easy to see that there you cannot put x to 0. And the reason you can't put x to 0 there goes back to this Gauss's law. Gauss's law tells us that past plus future minus left minus right is the charge. But if everything is positive and the charge is positive, I can't put both the past and future corners to 0 because then I have the sum of two negative things equals something positive. So I learned that this red region, I can't put anything to 0 in this red region. But furthermore, using the Gauss's law, I can completely determine everything in these red regions by the values on their boundaries. And therefore, in order to completely characterize what this space looks like, where I put x star to 0, it's exactly the same as a solution, another solution of the wave equation, where I simply scrunch away those regions. But you see, if I scrunch away those regions, what am I left with? I'm left with the product of two triangles, exactly the same problem, which has a 0 here and there, which is the x star point, and this is 0 and still 0 there. So you see that I get exactly the product of two smaller triangles of precisely the same type. So that's the sort of magic here, is that this picture of positive solutions of the wave equation makes it manifest that there's a polytope that factorizes on its boundaries. So that was what we were trying to make. That's what we're trying to make obvious. And the scattering amplitude, again, is really a scattering form. And what is the scattering form? Well, on the space of all these xij's, so you pick any n that you like, you draw the light cones out, and you draw all the light rays out, so we get all these interior xij's. So the form is completely fixed by this requirement that there's this sort of n-3 form that lives on this large kinematical space, but it has a property, is nailed by the property that when you pull it back on the solution of the wave equation, you get the canonical form of the corresponding associahedra, which is just what we saw. Okay, so now we've seen an example. So we go to the kinematic space. We kind of observe that despite appearances, it has some structure to it, has some causal structure to it. We ask a simple dynamical question involving the wave equation in this kinematical space. That brings to life this positive region, this positive geometry, and then the form is actually a form that lives in a huge high-dimensional kinematic space, but it has the property that when it's pulled back to the solution of the wave equation, it gives me the canonical form of the corresponding positive geometry. So that's the way in which we are getting these objects that have both locality and unitarity in them. In this very simple example already at tree level, from these more unfamiliar but still rather simple and interesting questions in kinematic space. So this is something that's trivially projective invariant. I don't have time to explain this in detail, but it essentially trivially explains why it's possible on the subspace that all the signs go away and we just get just plus signs adding up everything, and we literally get the amplitude. Now, that's the geometry. I told you what the canonical form is. Now we can finally ask, how do we get the canonical form? And I've already told you one way to get the canonical form for this class of polytopes is this triangulation where you add the line at infinity and you take the d log of the, you wedge the d log of all the variables meeting at a vertex. If you take that method for triangulation and apply it to the associahedron, that method is known as Feynman diagrams. And that should be obvious because it's something that's tied to every vertex. And if you remember, every vertex was precisely one of the Feynman diagrams. So this is a way of getting the final answer out of summing over all diagrams. But as I stressed already a few times, this has spurious poles. It has a spurious pole at infinity, term by term, that only cancels in the full sum. And that's why the Feynman diagrams obscure projective invariance. Every term breaks projective invariance. Only the sum over all the terms manifests the projective invariance. And in fact, there are many other triangulations of the associahedron. There are actually geometrically more natural triangulations of the associahedron that manifest a projective invariance term by term. And that leads to actually vastly more efficient calculations of even these tree amplitudes for phi-cube theory than Feynman diagrams. And that, I have to say, was a surprise for me. I had a prejudice in this subject for a long time that all the simplicity had to do with gauge redundancy, and and that there's nothing interesting going on in simple scalar theories. But maybe in Yang-Mills and gravity there was a lot going on, and it's not true that even simple scalar theories there's something missing. Feynman diagrams are vastly more inefficient than they need to be in the even for actual computations. So, but again, it's not for a random reason. It's because these other triangulations are more tied to the actual structure of the associahedron. They're not this They're not some random triangulation that would work for any old polytope that you then specialize in the case of the association. You do that, you get Feynman diagrams. No, there's something that's sort of tailored to the structure of the association itself, and that's what lets you arrive at these much simpler recursion relations and so on. All right.
Hello, Nima.
Yes.
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 Sorry. So this is a question about your previous slide.
Yes.
So so for this wave equation picture, is it important that there is a finite number of points, or I can just
no? Well, no. I mean, if you like, the way I described it is that you have the sort of continuum wave equation, and then you're just sort of sampling at a finite number of points. You can sample at however many points you like. So there's, it is an interesting question to try to intrinsically say something continuous, and that's also mathematically interesting. I could spend some time talking about it. I mean, the sort of intrinsically finite way of saying what the sort of continuous infinite associahedra looks like begins to bring to life what you can think of as time-like curves in this space-time. Observer geodesics in the space-time and so on. Causal trajectories in the space-time. So in principle, you could try to talk about it directly in the continuum. But if you want to talk about the amplitudes for a finite number of particles, then you're just sampling at a finite number of places.
Okay. And second question is that, is there a generalization of this picture to higher dimensions than 2? Or is there...
Notice that I should have stressed this. Notice that that the amplitudes that we're talking about are for phi cube theory in any number of dimensions.
Yes,
because in fact, these kinematic variables are just Mandelstams, and in really precisely in infinitely many dimensions, because I'm not keeping track of the fact that they have relations between each other.
Yeah.
There are these so-called grand determinant relations that just say that d+1 momenta are not independent in d dimensions. So I'm ignoring all of those. So in the sense of talking about really the phi cube amplitude in any number of dimensions, but really precisely in infinitely many dimensions. Where did the 2 come from here? So we all of a sudden seeing all these 2-dimensional pictures. The 2 came from the fact that that the natural kinematic invariants involve pairs of particles, Mandelstams, dot products of pairs of particles. So the sort of 2-ness in this problem has nothing to do with the dimensionality of the space-time or things are scattering, but has to do with the fact that the natural invariants involve pairs of particles. And again, as I said in my answer to Shiraz's question, one of Shiraz's questions, this is there are ways of talking about the kinematical space that just talks about one momentum at a time. That's what we do in the story of the amplituhedron, and trying to see how these things are related to each other is interesting ongoing work. I don't have very much to say about it, but this very simple story that you just get this 1+1 dimensional space-time and nothing else is for tree amplitudes. And then as we go on to all loop order and all orders in 1/n, the space-time, this kinematic space-time gets more and more interesting, and that's really that's the rest of the story of this talk. But anyway, I'm not gonna. I'm already really at the end of the time, even extra. So, but did that answer your question?
Yes, thanks.
Oh, okay, great. So let me just say just a couple other things, and I'll just maybe flash a few things, perhaps just as some indication for what I'll talk about in more detail in a couple of weeks, and then we can stop. Thank you for your patience. So I want to make one other point, which is that that we found in the past year or so. We found other general methods. I mean, we found a number of general methods for computing the canonical forms of polytopes. And one such general method has a parameter alpha prime associated with it. Now, this parameter alpha prime has nothing to do with string theory. It's just it's something Euler did back in the 1700s. It's just generalizations of things that Euler and Gelfand and other people did. So there's a general method that we call stringy canonical forms that you can apply to any old polytope, and it gives you as alpha prime goes to 0, gives you the canonical form, but it deforms it in some nice way when alpha prime is non-vanishing. Beautifully, when you take that general method and apply it to this particular associahedron coming from kinematic space, what you get is the open string amplitude, the Kobe-Nielsen formula for an open string amplitude. This picture in kinematic space, there's one triangulation of the associahedron that lets you see that it's Feynman diagrams. There's another determination of the canonical form that lets you generalize to string amplitudes. There are many others that let you see other things that are not obvious from either one of those two pictures either. So it's a sort of more invariant, it's a more invariant primitive structure that doesn't use any of these auxiliary spaces. The auxiliary spaces are used as part of the calculation of the form, but the form itself is sort of canonically defined and has nothing to do with any of those auxiliary structures. All right. Okay, so I think that's all I have time to talk about in any detail. Perhaps what I can do, so I won't go through this. Let me just flash a few pictures, and then we can stop. So let's say you want to move on from tree level to talk about one loop. So let's say I'm talking about this kind of box diagram for 4 external particles. So once again, you start drawing the Feynman diagram. The dual of the Feynman diagram is now again a triangulation of a square, but because I have a loop inside, it's a square that has a hole or a puncture inside. Okay, and so that's what we care about at one loop, is triangulations of polygons with a puncture inside. Now you do exactly the same thing. You just follow your nose. What are the kinematic variables? Well, again, I have these xij. Now the xij is not necessarily equal to xji because I can go from 1 to 4 or 4 to 1, winding one way or the other way around the puncture. Then I have these new variables that go from the outside to the puncture that you can think of, which are the sort of dual to actual loops, like we see in this picture. Then you have to actually think a little bit how you deal with tadpole diagrams and so on. So I don't have. This is a simple thing that I don't have time to talk about it in detail. But anyway, the point is the same. We have variables that look like xij, now not xji, slightly richer. I have these new variables y. Then you just go and you follow your nose and you plunk them down, and you again get a kinematical spacetime. Now it's slightly decorated it's slightly decorated. It's like I have a brain on one end of the space with some extra degrees of freedom. But anyway, it really basically follows automatically from just thinking about what the kinematic space is, and you just do the same thing. You draw the picture, you write down the analog of the wave equation, the analog of those Gauss's law relations, and beautifully what you get again is a polytope, and the canonical form of that polytope calculates the one loop, the integrand for the one loop amplitudes. Okay, so again, there is a polytope whose vertices are all the one loop diagrams. And where does this thing come from? It comes from, again, this picture of a slightly enriched kinematic space that has some extra variables associated with it. In general, if we are interested in H-trace Feynman diagrams that we draw on genus G and at L loops, then the dual of the diagram is a triangulation of almost the same surface, but it's a triangulation of that surface with H boundaries, genus G, and some fixed number of punctures, L plus 1 minus 2G minus H punctures. Okay, so in other words, we're interested in triangulations of triangulations of surfaces of genus G with some number of punctures. So here's an example. If I take a non-planar vacuum graph that I'd normally draw on a torus, then the dual of that diagram is still drawn on a torus, but once punctured. So that's what we're interested in general. And as I said, nowhere in the story did I say the word cluster algebra, but it pays to know that it's behind the scenes going on in all of this stuff. And again, in the lectures in a couple of weeks, I will give a completely systematic, self-contained introduction to cluster algebras. But there's anyway, I won't say more about that here. But what we're interested in is to, so now if we're interested in all loop order and all orders in 1 over n, Then we have trees and one loop, we've seen already, are associated with triangulations of surfaces and surfaces with one puncture. But when we go beyond two loops, high orders in one of n, we have more punctures and higher genus. And now, but this defines our kinematic space. Okay, so this defines our kinematic space. All the kind of chords that we can draw in this picture defines our kinematic space. And here there is a novelty. So I'll skip over all of this. Here there's a novelty that starts at two loops and higher, which is that a given Feynman diagram is not dual to a unique, does not have a unique dual because of the action of the mapping class group on the picture. Or if I say it more simply, let's say I'm interested in two loops. I have a bunch of points on the outside. I'm interested in the two loops. Then I have this variable, which is one of the loop variables, dual to one of the loop variables that I like. But I can go from the outside to the inside in many ways, winding around the other puncture. This winding is not sort of seen at the level of Feynman diagram, but it's sort of a crucial part of the picture in this dual. Clearly, you can wind around arbitrarily. In fact, if you have L loops, this is simply reflecting the action of the mapping class group, which is the braid group on L punctures on the inside. And so somehow we have to figure out how to deal with this infinity, mod out by the action of the mapping class group, and figure out what we're doing. That's exactly what we've been trying to understand over the past 4 months or so. And there seems to be an answer that generalizes all the things that we talked about before to things that we're calling Clusterhedra. And one of the fascinating things, just qualitative things, and again, I'll come back and explain this to those who are interested in a couple of weeks, is that in order to make this story work, we are forced to add new variables that do not show up naively in these Feynman diagrams. So everything in the Feynman diagram are sort of chords that connects points to each other. But in order to deal with this mapping class group, make the space compact and allow these polytopes to come to life, we have to add variables like this that are closed loops in the surface. So they don't show up in the triangulations, but they're a crucial part of the story. And once you add them, then you can go back to simple pictures. Like, if I want to talk about this first interesting example, which would be, for instance, double trace at one loop, is an annulus like that. If I want to deal with this example, there are obvious kinds of variables, kinematic space variables. I have these variables that go from the outside to the outside, or the inside to the inside. I have variables that go from the outside to the inside that wind around arbitrarily much. I have these new interesting variables, delta, that just are closed loops, correspond to closed loops in the surface. And with all of them together, if you once again follow your nose, look at the kinematic space, look at the analog of the wave equation, you get more interesting kinematic spacetimes. So the more interesting kinematic spacetimes have parts that come from these different regions, from the chords connecting the in to the out, the chords connecting out, and in. And if you didn't have delta, you couldn't glue these regions together to make a finite compact space. But delta is kind of like gravity. It couples all the sectors and it allows these clusterhedra to come to life. We're actually in the middle of investigating whether this analogy with gravity is more than a rough analogy. There's some more precise senses in which these deltas look like gravity. And it's sort of interesting that the deltas emerge here in the same place they emerge in open string theory at one loop in the annulus diagram. In the double trace parts of the amplitudes at one loop. But anyway, to those of you who are interested, in a couple of weeks, I will talk more about what these clusterhedra are. And maybe I'll just say one more thing. When you go to beyond the planar limit, when you start talking about, for example, even the once punctured torus, there's a really new thing and even one extra new thing that happens, which is that this kinematic space is not static. Everything I told you is sort of infinite, but in a very precise way, this kinematic space is growing cosmologically. So if you just look at all the loops you can draw on the torus, there's a precise sense where you can sort of associate them with these fairy diagrams, and there's a precise sense in which the kinematic space becomes cosmological, and anyway, this idea of these closed loops on the surface variables rescuing the structure continues to be the case, and we're understanding it better. But I'm just saying these things just at a qualitative level, that these kinematic spaces start becoming much richer than you would naively expect. And questions of quote unquote dynamics to determine these clusterhedra there become correspondingly richer, and the clusterhedra become richer as well. A final example is if you just have 3 punctures. So this is 3 loops, even on these would be sort of tadpole 3-loop diagrams, literally what I've drawn. Here, the kind of the action of the mapping class group, already we just have to label these, we have to label our arcs in how they connect the points on the inside to the points to the punctures on the inside. Already the labeling here is associated with the cosets of the braid group. So when I go from the outside to point 1, then I can act with all the cosets of the braid group acting on the 3 punctures modulo the ones that just rotate 2 and 3 around. And this is already some very interesting non-abelian structure. Literally, this is the free group on 2 elements. And so everything that I can make, even just labeling all the arcs, involves a picture like this, a Cayley diagram for the free group on 2 elements that also looks cosmological, but not just like de Sitter space, more like eternal inflation, where you get more and more of this sort of this self-similar structure repeating. And again, there's some interesting, this is associated with a clusterhedron structure that we're in the middle of understanding properly. Anyway, that was just purely pictures and impressionistic at the end, but the sort of big picture is that the kinematic space of these examples, even at tree level, despite seemingly has no structure, just the fact that some very primitive combinatorial facts about the kinematic space puts just enough structure on it in order to enable all these things to begin to start emerging. All right, so let me just end. Over the past few years, we've been seeing, I think, quite concrete examples. They're baby examples, but they're concrete examples where the rules of space-time and quantum mechanics, locality and unitarity, are seen to emerge from some simple new structures in kinematical space at infinity. And as I said, this really started with a new way of thinking about what the amplituhedron itself is in n=4 super-Yang-Mills. And you might say that, well, that's a very special theory, supersymmetric, integrable, blah, 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 planar. And yeah, I mean, I have to say that those of us working on it, certainly the integrability seems to have absolutely nothing to do with what's going on. But anyway, it's true that it was for that story. But I think now we're seeing it in totally non-supersymmetric examples. As I said, we've seen it sort of concretely. These clusterhedra are under control totally through 2 loops. Some 1/n corrections, all loop classes of cuts, but I think the sort of general, we don't fully understand the entire mathematical structure yet, but I think we're pretty confident that this is going to extend for triangulations of surfaces of any genus, in which case we would have all loop and all orders in 1/n for this phi cube theory. And this phi cube theory has the same factorization structure as Yang-Mills theory. It's something universal about factorization structure for any theory with color. And just to say again, what I like about this set of ideas, there's a lot of weaknesses. It's just about perturbation theory, blah, blah, blah. But they're directly related to the real world. That matters to me a lot. I mean, I'm sort of old-fashioned that way, but it matters to me a lot that it relate to the world we see outside the window when we look. It's related to that real-world physics in reasonable approximation. It exposes hidden symmetries and describes, as I said, universal features of a wide class of theories. Now, how are these ideas related? The ones that we've seen already between the amplituhedron and these new clusterhedra, we don't know. They clearly have some close relation to string theory. I've alluded to some of them. obviously we have these Riemann surfaces sitting in both pictures. They're not identical, and the sort of cluster structure associated with surfaces is something new, and is a deeper structure underlying Teichmuller space. That's one of the reasons mathematicians have been excited by it. But clearly it should be related to a string theory in a more direct and interesting way, perhaps. Is this analogy between these new variables that were forced on us, these closed loop variables on the surface that are forced on us, which are kind of vaguely analogous to gravity, is that more than a vague analogy? That's something that we're sort of actively looking at. And finally, of course, how do we extend these things to more general theories? I mentioned already the sort of very nice work on the phi to the 4 and phi to the p theories, extensions. How do those work at loop level? How do they connect with the story of clusters and surfaces and so on? That's all waiting to be done. So thank you very much, and thank you for your patience letting me go on so long.
Thanks a lot, Nima. Thanks for the wonderful talk. Maybe we can all clap for Nima. Unmute ourselves first. Okay, so I guess we can have more questions at this point.
Nima, I have a question. So for massive particles, is there a guiding principle to construct the canonical forms? Would it still be projective, and would it still be logarithmic?
Sure. I mean, you know, as you'd expect for scalar theories, mass is no big deal.
Yeah.
I didn't have to make it. I could have made it massive too. All that matters is that the xi plus 1s are fixed to constants, but
right.
They don't have to be 0. So of course, it doesn't matter there. Of course, for gauge theories, it does make a difference. And here I'm going to make the following conjecture. So there has been, I mean, there was a kind of a dumb obstacle for many years of there's sort of a dumb obstacle that there was no decent sort of analog of the spinor helicity formalism for massive particles. It's a essentially trivial exercise, but that has been done. And so there is a nice massive spinor helicity formalism for, and anyway, it's extremely simple. It should have been done 30 years ago, but anyway. So that's not the interesting part. My conjecture is that things will get better when they're massive. And we'll see more simplicity and more structure. And it's just that we haven't, you know, we have to get used to it a little bit. But one obvious reason for it is something that was seen already in this paper doing the massive spinor helicity formalism. The Higgs mechanism has a very pretty interpretation in this on-shell way of thinking about things. And you can think of it as an analog of grand unification in the infrared. So, you know, when we have massless particles, they're all different. All the different helicity components are different. When we Higgs, we're taking many different helicity components, where the little group is many products of U1, and we're unifying them into multiplets of SU2, which are, and that unification is rather manifestly seen at the level of the formulas. So you can really see that you have a kind of a smaller formula that takes the different helicity sectors and unifies them together. So I think things could get better when they're massive, but we just have to start seeing what the data looks like. And probably the best place to see that happen will be on the Coulomb branch of n equals 4 super Yang Mills. The Coulomb branch of n equals 4 super Yang Mills, for years and years, people have done very preliminary investigations of what the amplitudes look like, but there's clearly some tantalizing link between the Coulomb branch of n equals 4 and the so-called symplectic positive Grassmannian. Now, in the story of total positivity, there's the positive Grassmannian, kind of for SUN, if you like, or GLN. There's the orthogonal positive Grassmannian, which is, so the positive Grassmannian is for n equals 4. The orthogonal positive Grassmannian is about ABJM theory, but the symplectic positive Grassmannian, even purely mathematically, is clearly the king of these guys. It sort of sits on top. There's a sort of tantalizing links between this and amplitudes on the Coulomb branch, but it's not, anyway, there's some work to be done to try to make it precise. But my feeling is that in general, not just for these very special theories, but in general, when it's massive for gauge theories, it'll become better. simply because we're unifying more things. And also these sort of indirect hints that the kind of deeper structure in the sort of positivity world is in the symplectic positive Grassmannian. And what we've been understanding a lot on the on the GLN side is breaking this more unified structure up into different helicity sectors. Yeah, but for scalar theories, it makes no difference at all. They could have been massive.
Yeah. Thank you. Thanks a lot.
Sorry, could I ask?
Sure. Yeah.
Yeah. This is a follow-up on Spenta's question earlier in the talk. You gave us this construction associated with these polygons of polytopes and form associated with them. And is it fair to say, is it accurate to say that if you think of tree-level scattering amplitudes, going back to the beginning of your talk, if you think of tree-level scattering amplitudes, there's some numbers associated with momenta that have to obey certain consistency conditions. This beautiful geometrical construction gives you one solution to these, to the constraints of what an amplitude is. And it's a solution that picks out a very particular theory, namely this bi-adjoint scalar theory. And then would you then expect, other constructions for other theories? Also, would you, since this very nice structure came out for this particular theory, is that a theory we should be that there's any other reason to be interested in for some reason? Has it come up in some other context in some good way?
So let me say this point again. I'll give maybe I'll say I'll say in slightly more detail what I started saying in the answer to Spenta. Take any theory with color, okay? So that this ordering makes sense, even at tree level, okay, Shiraz? 5 to the 4, any number of derivatives, anything you want, random theory, 5 to the 17. Every single one of these theories has the pole structure of the phi cube theory. It's all contained, right? Every single pole structure we can possibly, now maybe some of them are missing, like if I have just quartic interactions, obviously I'm going to be missing some of them, but all the possible factorization structures that you can have are captured by this geometry. That's true at tree level, it's true at loop level. So there's it's true at loop level when we talk about the integrand. So before we get to the form and so on, so I'm just trying to make this, I'm trying to separate two things. One of them is just a kind of a surprising, purely almost combinatorial fact, that if I look at all the possible poles that can come together that reflect sort of local space-time processes for any random theory, that they're all captured by the vertices of these interesting objects. Okay, so that's the first statement, and it's universal true for any theory. The second thing is, what do you do with it? Okay, so that's a surprising and interesting fact. For some classes of theories, like the phi cube theory, then if you just match those singularities and nothing else, that completely fixes the theory. Okay, so one thing you can do with it is look for these forms of logarithmic singularities on the boundary of this geometry, and that totally determines it. But one natural thought is that maybe there are other ways of associating forms. For example, maybe what you should do is have a form that isn't just logarithmic, but after you take a bunch of residues, you can't go all the way to the bottom to find vertices. You stop at some codimension, but maybe where you stop, you have to match something. You have to match some pre-given form, that lower form that makes sense on that surface. So that would roughly be like, in the case that we're talking about, you go all the way down to vertices, and you're sort of, and there you're just matching the coupling constant. But in more complicated theories, you'd have to stop somewhere and match something else that's not just a constant, but reflects the momentum dependence of the 4-particle scattering or the 5-particle scattering or whatever. I'm just throwing out one sort of possible idea. Another idea, which is
this is right. There would be a one-to-one map between Lagrangians, modulo field redefinitions, and these forms.
That's right, exactly. That's sort of, I mean, I think that's my personal picture for what we should be trying to do, is exactly that. Exactly. We have Lagrangians, modulo field redefinitions, and some extensions of these forms that are not just D-log forms anymore. And the reason I say that is that we've just seen all over the place that when we go to less supersymmetric theories, other contexts, that we still have this structure, this geometric structure, and we have something else. We have another part of the space, other kinds of singularities, not just D-logs. And we've seen that just so much over the past decade that but just has not been explored. So so that's my feeling. Of course, there are other things you could do, which is what this work on Stokes polytopes and auxilliary and so on. That's the more straightforwardly, you could just say, look, you have different kinds of triangulations. If you have quadrangulations, if you have 5 to the 4, you have higher things. And it's very interesting that there is a geometric structure associated with them too. But this issue of needing to do something with the forms not quite being D-log doesn't really go away. There in that story, you have to combine different geometries together with some particular coefficient in order for the answer, in order to get the answer you want. And there's some nice work that even tells you why you're combining them in that way, the natural mathematical reasons to combine them in that way. But one way or another, we have to move away from this sort of addiction to the D-log form as a way of connecting geometry to a physics. But I just wanted to stress again, there is something sitting. I mean, there's this independently highly non-trivial fact that the sort of singularity, that the universal singularity structure for any theory, any colored theory, is captured by these kinds of geometries. And if I can just say one more thing quickly, because now in this language, I can tell you kind of what the amplituhedra is about. So these associahedra, generalized associahedra, clusterhedra are about the universal long distance kind of factorizations that you expect in color theories. And that's true in any theory with color. But Yang-Mills theory has more. It has soft singularities as well. And so if you demand that everything is seen geometrically, then there is an object in 4 dimensions that captures not just factorization, but every singularity, including the softs to the bitter end. The fascinating thing is that object is not polytopal. And that's the amplituhedra. So that's what the amplituhedra is doing, is it's universally capturing all of those singularities, including the soft one, that forces you to go beyond the world of polytopes into richer, simpler in many ways, but richer in other ways, positive geometry.
I have a question, Nima. Since you raised the point about the Higgs mechanism, I mean, we know that the universe, very early universe, is in a symmetry restored phase. So in some sense, would these internal structure, these mathematical structures of these amplitudes reflect that type of phase transition? Or I mean, it's a very futuristic question.
But just maybe I can just say this, that of course, when we're talking about amplitudes, we're talking about flat space. So we don't of course we don't directly see things like that. I will say though that so yeah, I think the short answer to your question is no, we don't know how to think about. I mean, this is really all about sort of boundary observables. Even if we're doing cosmology from this point of view, we're talking about cosmological correlations in the late universe. Of course, any physicist with a pulse cares about non-boundary questions, and 99.999% of physics is about these non-boundary questions. So and of course, what we do is we take these Lagrangians and so on that you can think of as forcing scattering amplitudes or giving a description of scattering amplitudes, and then we use them elsewhere, and we get the right answer when we use them elsewhere. So so yeah, that general thing I don't have anything to say about. But the more specific thing I want to say about the Higgs mechanism is that this Armstrong way of thinking about the Higgs mechanism is really, it's somewhat different. It's not, I mean, you don't see any fields, you don't see a VEV, you don't see any of those off-shell ideas. And it's also different than the bottom-up way of thinking about the Higgs mechanism, where you have to add something to unitarize WW scattering. This is really something natural from the top down, that if you have all the massless amplitudes in the standard model, then you can just ask, is it possible to sort of infrared deform them in such a way that I unify many different ones into a smaller number of massive ones? And that kind of consistent infrared deformation is the sort of natural on-shell picture that you get for the Higgs mechanism from this point of view. And it's that picture that I suspect should work very, very nicely on the Coulomb branch for n=4, even though it hasn't been done yet.
Thank you.
Nima, can I ask a question?
Yes, Logan, nice seeing you.
Oh, okay. Nice seeing you too. Yeah. So this is about your statement that when you include loops, you start thinking about things with punctures.
Yes.
I was just wondering. So of course, loops don't just have poles. You know, once you start going to loops, you have branches and so on and so forth. So should I think of these punctures as somehow encoding the very complicated branch cut structures?
Not yet. Not yet. I mean, I'm sorry that this part went kind of quickly, but this story is about the integrand for the amplitudes. So they're still just rational functions, and we're not imagining doing the integrals yet. And so that's a sense in which it's still not perfect. It's still cheating a little. It's not the absolute pure kinematic space. You know, the absolute pure kinematic space is just the xij's and nothing else. Okay. And we saw at tree level what to do in the pure kinematic space, but at loop level, in the pure kinematic space, we would then have to ask some question that gives me polylogarithms and branch cuts and all that kind of stuff, right? That is still too hard. What we are doing here is talking about not quite the pure kinematic space, but kind of close. I mean, we add the variables to it that we would think of as the loop variables that we then integrate over. But now life is simpler because we still just have rational functions. But again, rational functions with a very intricate pole structure, where if you take cuts, if you take residues on the poles, we have to get the factorizations that are associated with the cutting rules. So if you like, the cutting rules are precise, and so we know what's supposed to happen when you cut. And it's very intricate, and we're looking for this other structure that's going to force it on us. We don't yet know what the branch cut structure looks like for general theories. That's a still famously hard problem. So the kind of question of looking for even for some kind of non-perturbative geometry in kinematic space is still in general an open one. But in n=4 Super-Yang-Mills, over the past few months, we're starting to have some proposals, at least for what the space should be, for what the non-perturbative space should be. Not for the phi-cube theory yet, but we have some proposals for what the non-perturbative space should be, and it's starting to be explored. In other words, we still don't even quite know what the space is, but once we know what the space is, our feeling is that there will be a natural question to ask in that space, whose answer will give us the non-perturbative scattering amplitude. That's the fantasy. And we would ultimately like to do the same thing for the phi-cube theory, but it's quite a bit further from that goal now. I suspect it'll happen for n=4 first. I think we're sort of on the hunt for n=4. It won't take long now. For phi-cubes, it's going to take a look. Yeah, we have to explore more. Did that answer your question, Logan? Is it?
Yes.
Yeah. Yeah. Thanks. So these punctures are really just what you see in the dual of the picture. So yeah, it's just that if you draw that box diagram and you draw its dual, you naturally see a triangulation of a square with a sort of puncture in the middle.
Okay, thanks.
Sorry, Nima, is this phi-cube theory well defined in 4 dimensions? Does it have an instability? Because, not that it matters to you.
No, again, I'm not integrating. So no, I mean, 4 dimensions we have terrible instabilities. In 6 dimensions, it could very well be well defined. In fact, I mean, not literally for this bi-adjoint theory, but this work of Klebanov and friends and maybe others talked about the vector phi-cube theory at large n, and they find evidence for a fixed point in 6 dimensions.
So the fact that it looks like it's benches unbounded from below does not the fact that
no, I mean, that's like the usual thing. I mean, for example, if you take negative phi-4 theory in 4 dimensions, then there is an instability that it goes like e to the minus 1 over lambda, right? So it's a non-perturbative instability. Phi cube theory, in 4 dimensions, the instability scale would be given by mu, I mean the scale of the phi cube coupling, but that's only because it's strongly coupled in the infrared. So when you have the like bubbles that would nucleate, the amplitude for nucleating the bubbles is large on the scale of order 1 over mu. In 6 dimensions, where the coupling is dimensionless, it's the same. It's exponentially small. And then it's like anything at large n. E to the minus 1 over g squared is e to the negative n over g squared n. So all of these effects go away in the strict large n limit. So it's possible that this theory is healthy in the strict large n limit and has no vacuum decay and so on. So that's kind of yeah. But I should say that would only likely be true literally in 6 dimensions, but nothing in what we're talking about knows about the dimensionality so far. So I really think of the phi cubed here as kind of a temporary stand-in for doing Yang-Mills. It's really, its purpose here is to allow us to see all of the graphs, combine them all, meaningfully talk about something where we're not yet forced to deal with this polarization vector issue in general.
Thank you.
Yeah, and as I said, that there's very strong relations, even with like just perturbative string theory, but a different way of thinking about perturbative string theory, perhaps. So that's another general motivation. I alluded to the fact that there's a sort of method for computing canonical forms with an alpha prime that, when applied to this example, gives us the Kobe-Nielsen formula at 1 loop. Well, I also told you that we already understand what these polytopes look like, sorry, at tree level, what these polytopes look like at 1 loop. And if you, instead of the AN cluster algebra, it's the DN cluster algebra polytope. But if you apply the same method, you get some object that has an alpha prime. It has all these magical stringy properties. It factorizes, it has channel duality, it has all these things that we normally ascribe to the stringy magic, but with no worldsheet in sight. And it looks like an integrand. Also, that's also not something we normally talk about in perturbative string theory, but we could sort of reverse the order in which we do various worldsheet integrals to be left with what you could call an integrand at 1 loop. And there's an open question whether this object that we define at 1 loop with an alpha prime, is it the same or not the same as what you get in string theory at 1 loop? And I think any answer would be interesting. If it's different, well, that would be really crazy to have multiple objects with an alpha prime in them that have the same magical properties. But if it's the same, it would be interesting too, because it's a way of getting the answer where you never see any theta functions, you never see the obvious worldsheet, but nonetheless, you get the answer another way. So I think those are the kind of possible link with string theory, as well as universal aspects of universal factorization type properties of Yang-Mills are what I really think of this structure is about right now.
And the connection with string theory was with the bosonic string, I presume.
No. You see, that's another thing. You see, when we have I really mean with Kobe-Nielsen type integrals. So precisely because we don't have polarization vectors and so on, then it's really the kind of worldsheet integrals that you would associate with the open superstring and the closed superstring too. But you know, whenever you do these manipulations, you know that the kind of polarization stuff comes out, and then the kind of guts of the stringy integral is some integral over the moduli space, and those integrals factorize, and they have all the wonderful properties that we talk about. It's really directly those integrals that are associated with these bi-adjoint theories. For example, you know, like literally Kobe-Nielsen, it's like the integral dz1, dz2, whatever, over the product of zi minus zi plus 1. and then the product of the zi minus dj to the alpha prime sij. So that integral, it's for massless external data, yeah. So that's the integral that alpha prime generalizes the bi-adjoint amplitudes at tree level. There are some, if you literally want to get the bi-adjoint theory, I think I forget exactly, but I think if you look at some compactification of the bosonic string on a circle with self-dual radius, then you can get a 3,3 of the SU2 cross SU2. And so that's a bi-adjoint of the 3,3, and you could look at the scattering amplitudes of that 3,3 state, the massless 3,3 state at tree level. Then that would match this, but it doesn't have an n that you can, I mean, it's literally for SU2 cross SU2.
Okay,
But,
thank you.
but the more general thing are the actual worldsheet integrals, which are doing all the heavy lifting. You have these worldsheet integrals that factorize, that do all the heavy lifting, and then we decorate them with polarization vectors to turn them into Yang-Mills amplitudes or gravity amplitudes. But the kind of heart of the structure of the moduli space and the factorization of the moduli space is captured by these simple scalar integrals.
Thank you very much for such an extended discussion.
Hello.
Thank you very much, guys. I really appreciate it, and thanks again for your patience. Thank you for letting me go so long over.
Can I ask a question, please?
Yes, there was another question. Yes.
Sir, I feel like although I'm in the intellectual space, but I am actually in postgraduate. I want to ask that how should I go about studying advanced topics? Now I'm in first year actually. How should I go about studying advanced topics? Like,
sorry, maybe you can speak up. I can't actually hear you.
Oh. Am I audible now?
Yes.
My question is that I am in postgraduate studies and I'm in first year. So my question is, how should I go about studying higher topics like string theory and higher topics like string theory? Can you give some tips about that?
I would look at all the classic textbooks and talk to people. I mean, you're a first year grad student, is that right?
Yes, sir. Yes, sir. I'm first year grad student.
Yeah. Well, I mean, there's very general advice, but is yeah, find every book you can, follow the archive every night. Yeah, throw yourself in and just swim like mad. And it's completely nonlinear and crazy process. So I have nothing. There's no general advice. Other than that, you should expect it to be tremendously challenging and fun and crazy. And just yeah, and find people to talk to. Yeah, there's no universal advice, unfortunately. If there was, physics would be much less interesting. It's completely different for everyone. And all I can say is you just have to work your ass off and find people to talk to. That's my only advice.
Thanks a lot, sir.
No problem.
Okay, do we have any other questions? Okay, if not, let's thank Nima again. Thanks a lot for taking the time out and giving us this extended talk. And we look forward to your lectures later this month at the ICTS.
Thank you very much. I really appreciate it. Thanks a lot, guys. Bye-bye now.
All right. Bye.
Bye, Spencer. Bye, Shiraz. Bye, Logan.
Bye.
Bye, Shivrat. I didn't say hi to you, Shivrat, but bye. Yeah. Right. Bye-bye now.